So I've had to continue this video because it just decided to stop working on me. So I'm back to question B, part 2 from 2017. We've already established that we know the concentration of the sodium hydroxide. We know the concentration of the ethanoic acid because we had that supplied in part 1. And what we've done is we've added 10 mils of the sodium hydroxide to the ethanoic acid. So we've diluted the ethanoic acid. Now what we've done here is we have neutralized some of our ethanoic acid. And we've neutralized it by using the strong base, and we've made the sodium ethanoate, and we've made water. But the thing is, we're not at equivalence point here, so there is still some ethanoic acid left. And we can figure out how much ethanoic acid is left by simply considering the dilution factor. And the dilution factor that affects the concentration of the ethanoic acid and the concentration of the ethanoate. So what we're talking about here is we're talking about a new diluted concentration. So the new diluted concentration of the ethanoic acid is going to be its original concentration, which was 0.166 moles per liter, and multiplied by the dilution factor, which is 20. We had 20 mils of it to begin with, and we've added 10 mils of the strong base, so it's now over a total volume of 30. So that's 2/3 of that concentration, which works out to be 0.1107 moles per liter. And then if we consider the new diluted concentration of the ethanoate, which we formed because we forced some of the weak acid to form that with strong base, we take the same concentration of the strong base, because what we're saying here is that the concentration of the base that we use at that point will form the same concentration of the weak conjugate base, and that's how we figure its concentration out. But of course it's also diluted, so we've 10 mils of that over 30, so it's 1/3 of that concentration, which works out to be 0.0373 moles per liter. Okay, so now we know the concentrations of our ethanoic acid and our ethanoate at this point on the titration curve. So we can just plug these numbers into our Ka expression. So the Ka expression, remember, is referring to the equilibrium of the weak acid and its conjugate base. And we want to know how this affects the concentration of the hydronium ions now. As you can imagine, the concentration of hydronium ions should have dropped compared to what we had in the first part of the question. Because, of course, we've neutralized some of our weak acid at this stage. And so if we continue with the calculation, the Ka value was given to us at the beginning, so that's 1.74 by 10 to the negative 5. The concentrations of these two components here, we've just worked those out above. So this should have been ethanoate, by the way. So CO minus. So the concentration of the ethanoate was 0.0375 when it was diluted moles per liter, and the concentration of the H3O plus we do not know. That's what we're trying to work out, and divided by the concentration of the ethanoic acid after it was diluted with the sodium hydroxide was that. And so if you do that calculation out, you should get a number which is 5.164 by 10 to the negative 5 moles per liter, and that equals the concentration of the hydronium ions. And then, of course, if you negative log to the base 10 of that, you should get a pH, and the pH for that works out to be 4.29. So 4.29 is not far off the predicted 4.80. So as I say, it was good just to read that off the graph as a general indicator of what your target number was for. But that is not a particularly easy question to do, and that was B part 2 in 2017. The last part of the question then, part C, is straightforward if you know how to do them. And a question like part C came up in 2015 as well. So I'll quickly do part C. I'll do it as a separate video.